Okay, now I'm recording. Let's start this over again. Okay, so if we have a list of size n, and we want to know whether or not something is in there, how many things we have to look at? And you all said n. Yes, and that's a linear time algorithm. Or yeah, your linear search, that's like your linear time algorithm. Order n, big O n. But it's important to note that, remember, when we think about linear, it means like the amount of work being done scales linearly relative to the size of like the input. In this case, it's n. There's n things in the list. So if we have n things in the list, if we double it to 2n, how much more work are we going to do? Twice as much. If we quadruple it, how much more work are we going to do? 4 times as much, right? It scales linearly as we increase the input size linearly, you know, as we like double it while the amount of work being done doubles. As opposed to quadratic. If something's like n squared, and we will see some searches that are n squared soon, but if you're doing an algorithm that's like n squared, you've got nested loops doing something, okay? Maybe you want to compare every number to every other number in your list. So that's like an n squared algorithm. And if something's big O of n squared, if it's quadratic, if you double the amount of work, no. If you double the size of n, how much more work do you need to do if it's n squared? Well, you have to do 4 times as much work. Because if the input size is n, the amount of work you have to do is n squared. If the input size is 2n, well, that's 4 times the amount of work because, you know, squared. So sometimes when we double the input size, it doesn't grow linearly relative to the input size. It grows at like n squared. And, you know, as n gets larger and larger and larger and larger and larger, this is going to become much more problematic if you have an algorithm that's n squared, because, you know, it might start taking too long to run or something. Fortunately, you know, a lot of our algorithms, you know, they'll be fine with something that's like quadratic. That's not that big of a deal. We like quadratic algorithms. They're not too bad. I mean, if we can find something that's linear time, even better. If we can find something that's like log n time, even better. If we can find something that's constant time, huzzah, that's the best thing, you know? But if you've got an algorithm, like if you wrote a linear search that took n squared amount of time, that's bad. Like, don't do that. I mean, anyone can do that. You can write a linear search that'll take n squared time. It would be absolutely useless. You could, like, for each number, look at all the other numbers for no reason and just keep doing it to see if you find something, right? Like, you could arbitrarily make your algorithms horrible relative to the size of n. But if you can do your linear search, or pardon me, if you can do your search in order n time, fantastic. But what if I told you, you could actually do that search way faster, right? What if I told you that, you know what, you can do your search through your collection, not in, like, how about this? If I had you double the amount of work, oh, no, I keep getting this backwards. If I had you double the size of n, wouldn't it be great if the amount of work you had to do didn't double, but it only increased by like 1? You know, wouldn't that be magical? I heard a boop. Hopefully someone didn't spoil it. 0.5n? No, even better. It's even better than 0.5n. Also, 0.5n is still linear, right? Because you remember, 0.5 is like a coefficient. We don't really care about coefficients. Dictionaries, well, with dictionaries, I like where your head is at, but dictionaries are good for like making things like constant time, usually. And they might not be great for this like search, but I'm going to show you a wonderful little toy example. And this whole time I've been meaning to, okay, let's say run number, yes, come on. Man, I think my computer's getting worse. All right, so what do we do here? What if I told you that I can guess? Oh, I heard another boop. What's the difference between a sorted list, a binary search, and binary search tree? All right, well, we're going to get there. We're going to get there, but you're asking the right questions here. That's a great question to ask in this context. So good job. Okay, what if I told you, okay, wait, what's no, 2 times 10. Yes. All right, perfect. No, what the heck is this called? Pardon me, I'm just trying to find... Ah, okay, here's what it is. Okay. I'm going to tell you that... Okay, if I gave you a list of size of all the numbers between 0 and 1023, don't think too hard about the fact that I put a 1023 in there. But if I were to tell you, if you had a list of sizes from all the numbers from 0 to 123, so there's or 123, 1023, so there's a total of 1024 things in that list, right? And I asked you, like, okay, does a certain number exist in there? And you're doing a linear search. How many things you're going to have to look at? Well, 1024. What if I told you, I can tell you whether or not something exists in that collection, in that group of information of size 1024. What if I told you I can find out if that number exists in no more than 10 guesses? What if I tell that to you in 10? No, don't look at that. Don't think too hard. Don't ruin the fun. Okay, actually, it's a good thing. But yeah, in 10 guesses. Okay? So here's what we're going to do. We're going to need a volunteer. Who wants to volunteer? Someone volunteer. Come on. Sure. All right. So here's what you're going to do. You're going to pick a number between 0 and 1023. Don't tell me what it is. Don't tell me. Just keep it in your mind. Okay? And I'm going to guess it in 10 or less numbers. So tell me when you're ready. Okay, you've got your number. But okay, here's the catch. Here's the one little catch. Here's one thing you got to give me, okay? If I guess a number and your number is higher, you have to tell me, okay, higher. Is that fair? That's fair, right? That's not too bad. It's easy. You know, if I say like, oh, is the number 50 and your number is like 70, will you be like, no, it's higher. Okay? All right, cool. So here's what we're going to do. So, my first guess, okay, is it 511? Higher. All right, it's higher. So that was guess 1. There. Is it 767? Lower, okay. Is it 639? 575. I can't see here. Let me move this out of there. There we go. Okay, that's. I'm trying to hold up 4 fingers. Apparently, I can't do that. Is it? Wait, I said 575. You said lower, right? Okay. 543. That's 5 guesses. Lower. 527. 519. 515. 513. So I got it then. Yay! Look at that. That was only 9 guesses. I got it even less than 10. Now, obviously, I shouldn't say obviously, there's a good chance you've kind of figured out what I did, right? Like, well, you just like guessed in the middle, and then if you said higher, just go halfway between where you were before and the upper bound, and just keep going halfway and narrow it down until you find what you're looking for. Right? So suddenly, instead of having to look at 1,024 things, I had to look at no more than 10 things to find it. So isn't that neat? So, you know what's crazy too? Is if I were to double that number, if I were to say 2048, right? If I said, okay, a number between 0 and 2047, right? So there's a total of 2048 numbers. So I doubled the numbers from 1024 to 2048. If I was doing a linear search, how much more work am I doing? Well, twice as much. If I'm doing this type of search that I'm doing here, it's only, I can guarantee I'll guess it in 11 or less guesses. And if I double it again, 12 guesses. Every time I double, I only have to do one more thing of work. If I were to say, pardon me while I clear up my screen here. If I were to say, hold on, I don't want to say it out loud because I don't want to spoil the fun. If I were to say I could guess a number between 0 and 1,048,575 in 20 guesses or less, I mean, that sounds unbelievable, right? But it's true. I could guess a number between 0 and a million plus change in less than 20 guesses or less. Isn't that crazy? It's only 20 things of work. Where if this was linear, it's over a million. I got to look at each of those things. Isn't that wonderful? But there's a catch. The catch is you got to tell me whether it's higher or lower. And it helps me narrow down my search. So, where's the magic? All right, so let's switch to the actual lecture now that we're a good way into it. Why aren't you putting your thumb down for 4? Yeah, I don't know. That definitely would have been easier, wouldn't it? And I suspect Johannes knows the trick here, but anyways, don't look at that. Don't look at my cheating. Don't look at my cheating. Don't look. I didn't write code to help me make those guesses. All right, what did I see? Tried to make an edge case, didn't work. Yeah, all you had to have done is, if you said 512, you would have been good. Cheating, no, don't use mouse. All right, so where were we? What do we got here? I hear more boops, almost did. Searching a binary search tree. Okay, binary search tree. Yeah, what are we gonna do? Okay, searching a binary search tree. The special ordering of the binary search tree makes searches very efficient, right? Because all I have to do is, if I know that all the numbers on the left side, if I know all the numbers over here are going to be less than 10, and all the numbers over here are greater than 10, if I'm coming along and I'm looking for 11, well, I'm looking for 11. Which child should I go to? The left or the right? We'll go to the right, because 11's bigger than 10. So it's obviously in the right subtree if all the numbers in the right subtree are greater than 10. So here, we go to this one. I mean, there's nothing on the right subchild, but if I'm looking at 15 and I'm looking for 11, well, 11's less than 15, so I go to the left. Oh, I found it. Hooray. But if I were doing like an exhaustive search, imagine this tree had no ordering. Imagine if this was just a binary tree. Because, I've got the code here. Binary node. Where's my binary? Did I ever write the binary tree? Binary node. What? Did I not write array? Binary course. Okay, I guess I didn't write it. All right, well, that's fine, I guess. I swear I wrote like the find. I guess it was just in the slides. So if I just had an arbitrary tree where there was no ordering here, in the last set of slides, we saw a recursive algorithm to do a search through the tree. Basically, are you the thing I'm looking for? If you are, fantastic. Otherwise, do the search on the left subtree. If you found it, great. If not, do the search on the right subtree. And we had to do this because there was no guarantee of the ordering, right? I mean, I don't know, this number could have been 70 in a regular tree, for all I know. And so, there's no guarantee that everything to the left is smaller, everything to the right's greater. So if it's just a regular old binary tree, it's, are you what I'm looking for? Yes, no, otherwise search this subtree. If you find it, great, otherwise search this subtree. And then how do we do this one? Oh, is this what we're looking for? Yes or no? No, all right, search this subtree. If you found it, great, otherwise search this subtree. Okay, this one, is this it? No, search this. Oh, nothing, okay. Search this subtree. All right, is this what we're looking for? Yes, no, all right, search this subtree, and so on and so on and so on. So there's the recursive find. But here, oh, sheesh. Look at this, I've already got this. All right, so if the tree is not empty, if the data is at the root of the tree slash subtree, if this is what we're looking for, we found it. Otherwise, search the left subtree, search the right subtree. What is the computational complexity of this if there are n nodes in the tree? Remember, n is the number of nodes in this context. So how many things am I going to have to look at to guarantee whether or not I found the item I'm looking for in a regular old boring binary tree? I should say binary. Let's see, n, exactly, it's n. You got to look at all of them. You won't know whether or not you found the thing you're looking for until you've looked at all nodes. But here, we get to do something better. If the tree's not empty, if the data is at the root, we're done. Otherwise, if the data is less than the root, then search the left subtree only. Because if it's not in the left subtree, it's obviously not in the right subtree because those numbers are bigger, and we know that the thing we're looking for is smaller than the root node of the tree slash subtree. But if it's larger, search the right subtree. What's the computational complexity of this? And I have a feeling Johannes knows. And here, this one, the way this is written, this assumes that there are no duplicates, but it's easy to change by saying, well, if the data is larger or equal to. There. So what's the computational complexity of this? Big O of what? Any ideas? Log base 2n, exactly, 100% correct. Why is that? Well, every time, if we have n nodes, and we're going here, and we have a choice to go left or right, and assume this tree is relatively balanced, right? If I make the decision to go left, I've effectively thrown away half minus 1, but half of the nodes. So after making one decision, I've got roughly, so I've gone from n nodes I need to look at to roughly n over 2. And then after I do another decision to go left or right, I hate this. I don't know what's going on with this computer. N over 4. And then if we do that again, n over 8. And you might see the pattern. We're like dividing by 2, dividing by 2, dividing by 2. Well, a lot of people, I don't know about you, but I always had a hard time with logs. This is why I like log base 2, because it's easier. Maybe that's why I could stand computer science. But I know you know, well, if you keep doubling, like if you keep doing multiplication over and over and over and over and over again, that's like exponent, right? Just like, okay, if you keep doing additions, that's kind of like multiplication. If you keep doing multiplications, that's like exponent. Well, if you keep doing divisions by a certain number, that's the log. And what the division, I mean, that's the base. Log base 2, because we're dividing by 2 every time of whatever n is. So that's the pattern here. So let's follow this. What am I looking for? We're searching for 13. Okay? So 8, 12, 9. Okay. Visit nodes are colored bluish, return false, and node continue. What? All right. So this is doing too much at once. If I go here and I'm looking at 14, which way should I go? Well, 13 is less than 14, so I go over here. So now I'm here. I'm looking at 8, but I'm looking for 13. Should I go left or right? Well, I know that 13 is bigger than 8, so I should go down to this one. And then, okay, I'm looking at 13. I'm looking for 13, but I'm looking at a 12, so I should go to the right. Oh, well, there's nothing there. And if there's nothing here, 13 can't be in this tree. I can very safely tell you 13's not in this tree if it was built correctly. This of course assumes this is in fact a binary search tree. If someone put a 13 here, after the 9, well, this search wouldn't work, but also this would not be a binary search tree because 13 is bigger than 12, and what's it doing in the left subtree? So let's erase, try to erase everything. So there, we conclude it's not there, but that looks for 22. All right, 22, well, that's bigger than 14, so we go this way. 22 is less than 26, so we go here. 22 is greater than 19, so we go here. 22 is less than 23, so we go here. Oh, there's nothing there. Therefore, we know 22 cannot be in this tree. You know what? Let's do a search for something that is in the tree. Let's say we're now looking for 9. So 9, well, that's less than 14. 8, well, 9's greater than 8. 12. All right, well, 9 is less than 12, so it must be in the left. 9. Oh, we found it. Yay. Fantastic. Yay, we found it. Every time, if this was a complete tree where it was nicely filled like this, I'll do one more. 1, 2, 3, 4, 5, 6, 7, 8. There. If we had something like this, if I go left, look, I'll only have 1, 2, 3, 4, 5, 6, 7 more things to look at because I was able to throw away 7 over here. So, I mean, originally there's 15 because we got 7, 7, and then this one. But every time we make a decision, we're throwing away half the nodes. We are dividing the amount of work we have to do by 2. So divide, 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 divide. Yeah. Okay. So here's the code for it. And it's, if the current node is a null pointer, basically if you exist or not. If you're not, or no, if you are a null pointer, if you don't exist, return false. Because if this thing doesn't exist, it's not what we're looking for. That's easy. If this is confusing you, you're thinking way too hard. If you don't exist, you clearly aren't number 13 because you're nothing. Otherwise, if the data is the thing I'm looking for, oh, return true. Fantastic. We found it. Otherwise, if data is less than the thing that we're currently looking at, just do a recursive call on binary search on the left subtree. Left. Because it must be in the left side. Otherwise, do it on the right. And then we'll have this like helper function here that basically just calls the search on the root there. So you'll notice that if we look at the pseudocode for the regular search, like the find function we wrote, or the contains for a regular tree, like a binary tree, not a binary search tree, it's going to look really similar to this. The only catch is instead of the else, it's like, well, if we didn't find it, look here. So where here, only one of these will run. In a regular find, both might run. And a good thing here is to think like, okay, you might remember, well, I know when he was talking before, when a recursive function had 2 recursive calls inside of it, that's when we're starting to think like exponential, you know? Well, you're right, but you know, in reality, although this has 2 function calls, only one will ever be run because we've got an if-else. They're mutually exclusive. All right, so if we wanted to add something to this binary tree, it's pretty simple. Just do the binary search until there's no more, until the child doesn't exist, and then it must go there. If that doesn't make sense, I'll show you an example. Okay, perfect. I want to add 13. All right, 13's less. 13's greater. 13's greater. Oh, nothing's here. 13 must go here. Fantastic. Let's add the number 11. All right, less than, greater than, less than, oh, so it must go here. 9, oh, it's greater than, so it must go here. 11. There. Let's add the number 99. All right, well, that goes over here now. And, well, clearly to the right, now we've got 99. Now let's add the number 50. All right, must go here. 50, and so on. So let's look at the code. If the tree's empty, insert the thing there. Otherwise, if it's not empty, if the data is at the root, this is what we're adding. Now, this implementation assumes no duplicates are allowed. There's an easy fix to make it duplicates. You just basically, usually what people will do is make it larger or equal to. If the data is less, go to the left. If it's bigger, go to the right. And just keep doing that until you find the empty spot and then add it there. Now I heard a boop. Is there any kind of tree that is able to have more than 2 child per root? Yes. It's just, I mean, an arbitrary tree can have as many as you want. You could have a tree with, like, I don't know, here's a note, here's a tree. There's a weird tree. This is the root. I mean, in this one, remember, so a tree has like an arity of the node with the maximum arity within the tree. So here, okay, we got 1, 3, 2, 1, 1, 2, 3, 4, 5, 2. So this tree here actually has arity 5, because this one has 5 children and it's the largest. But yeah, you can have a tree with as many as you want. Yeah. Oh, there's a 13. Are arrays of arrays technically trees? Well, I mean, an array is a tree itself, right? Because, well, let's think about that question. Because an array is like a unary tree, kind of. Well, not really an array, but let's say it's just a list. Let's do that, because that's easier. This is a tree. It's just each one only has 1 child. But if this one has an array in it, like, yeah, you could think of it as a tree. In fact, you can kind of think of it as a binary tree. All right, so yeah, what is this? Well, if the current's a null pointer, what we're going to do is you return the binary node with the data. So basically, if you found where it belongs, create a new binary node and put the data you want in there. If it's to the left, if it should be in the left, what we're going to do, and this might seem a little funny, but it checks out, don't worry. What we're going to do is we're going to call the recursive function here with the data. Pardon me, I missed the data bit. And we're actually going to set the left to that right there, to whatever this returns. Otherwise, it's the same thing, but on the right. And then at the end, we're going to return cur. Now, it might seem weird, like, wait, why are we... So we've got the recursive call. I'm going to erase the ink. We've got the recursive call here, but why are we setting the left to what this recursive call is like setting? And let's... I don't like this. So I'm gonna show the example. Oh, and then here's the helper one, where basically it just calls it on root, and we have to increase the size for our data structure that is like the binary search tree. Now, why is it returning? Well, let's just, if we draw it out, it should make good sense. So let's just say this is where we're going to want to insert some arbitrary number. So what we're going to do, okay, this isn't it, this isn't it, this isn't it. Here we go. Here's what we're going to do. So we are now on this line. We found where it belongs. So this is where, I'm going to change colors, I guess. Make it blue. This is where we inserted the thing. And what are we going to do? Well, we return this new binary node. So we go to the calling function, who did clearly a search on the left, because from here we went to the left. And what are we doing? Well, we're setting your left to what was just returned, which was this node. Fantastic. That's awesome. So now its left is that new node we just created. And then what are we going to do? Well, now we go here and then, oh, we return cur. But what is cur? Well, I mean, cur is a pointer to this node, right? So like cur is the node that we just set its left to. So if we return cur to the calling function clearly from here searched the right, it was here. So this right here returns this node. And what are we setting this one's right as? Well, this node. So basically, it seems weird, but all we're doing, except for the instance where we have the actual new node being created, where we're now saying, okay, you actually are new information, everyone else is being, like, everyone's left and right is being set to what their left and right already are, with the exception of the base case where we actually had to create a new node. And this is just the easy way to implement it. If you're having a really hard time with this one, just isn't that redundant? Well, how about this? You try to come up with a solution that's recursive that looks good like this. Well, it's redundant in the sense that it's setting left to be itself again, but it makes the implementation a lot easier. And this extra work being done is inconsequential. It's constant each time. Sure, we're doing constant time more work for the depth of the tree, but that's still not going to make it computationally really worse off. If you can come up with an implementation that's recursive that doesn't look like this and is this nice and pretty, go for it. But this is the easy implementation that, yeah, sure, we're reassigning it. You're totally right, but it's just easier to implement it this way. And then, yeah, okay. Here's an example of us adding stuff to the tree. Add 26. Okay, well, that's now the root of the tree because the tree started empty. Add 15, well, that goes to the left. Add 38, that goes to the right. 31 will go to the right, go to the left. 7, left, left, left. 34, right, left, right. Okay, great. Now, if we remove something, though, this gets hairy. Because what if I say remove 38? Well, I guess this doesn't seem too bad because I guess what I would do is I would get rid of 38 and then have like 26 go there, right? That saves it. But there are a couple of funny situations. If we want to get rid of a leaf node, that's easy. Get rid of 7. All right, there, done. The tree's still happy. If it's an interior node, we can't simply just change the link from the parent to the successor. Because what happens if we remove 26? What do we do? If we remove 26, one of these two is going to have to be promoted, right? If we promoted 38, well, okay. But then the 31 needs to go to the left side of the tree along with the 34 because the 38 actually ends up being the biggest number. So maybe the 31 should be, it's hairy. We can replace the node with its in order predecessor or successor. But I mean, this is where we're starting to get like, well, what about this and then that and then this and then that and all these funny things. But this is something you're going to learn next year in 255. This is something that's outside the scope of 162. Because this is where things can get hairy. Sometimes it's not bad, like in the previous example where, okay, I guess we can just, have that happening. But sometimes it can get hairy. Yeah. So if we remove 70, well, that's easy. There, gone. Remove 7. Well, here was the 7. Well, what are we going to do? If we remove 7, I guess 9 will have to be promoted. Remove 38. Well, what are we going to do? Well, it looks like one of the interesting ideas was to put 36 there. Huh. And it looks like if we do put 36 there, everyone's happy? Well, that's fun. Remove 26. Where's the 26? So that's the root. Who are we going to do? I guess it looks like 15 got promoted. Remove 31. Well, so there's 31. What are we going to do? Well, I guess, yeah, we can just do that. Yeah, and that all checks out. I heard a boop. Couldn't we put in a stack, remove the 1, and rebuild? Totally. We totally could do that. But I'm wondering, like, maybe there's a more efficient way to do it. But you're totally right. In fact, there might be a really good reason to do that. Kind of maybe. But we're going to talk a little bit about a problem shortly, actually. Will we get to it today? No, we will not. But that's okay. We'll get to it tomorrow. Okay. Remove minimum. Well, this one's easy. The leftmost node must be the smallest number in a binary search tree. So we know it's going to be like if it's a leaf, It's easy. Remove it and set its parent to null. Otherwise, I guess what we could do is, what do I say? Root has no left child. Okay, so this means if I had something like 8, right? So this is the minimum, the leftmost tree. So root is min, right subtree root is now the whole tree's root. Well, that's okay. So it looks like with remove min, all we have to do is get rid of the leftmost thing. And then if anything exists in its right subtree, because we know nothing exists in its left subtree, because that would mean that something smaller is over here. Because everything to the left of 7 must be less than 7. And if there's nothing there, therefore, yeah. And we know that's not the case because 7 is the smallest. So all we have to do is just promote its right subtree to the root. And I don't care how many things there are over here. If it's an interior node, remove it. Right child becomes parent's left child. Yeah. Becomes parent's right child. And then, so let's see. If we're removing the smallest, well, that's the 7. It gets cut. 9's promoted. Remove minimum again. Well, the 9 gets cut. So now we've got 15. Oh, 9 gets cut. Well, that was, wait, where are we going? Where are we going? 9 gets cut. We just remove it. Okay, cool. Now we want to remove 15. All right, well, cut it, but just do that. There. Now, this is where we're at. The 18 is the left. Remove again. All right. Get rid of the 18. Remove the minimum again. All right, well, get rid of that. And now this is the root and so on. Are we going to remove again? I guess we, if we remove minimum again, get rid of that. Remove minimum, that, and then this becomes the root. Remove minimum, now we've got an empty tree. Remove max, the same idea, just in reverse. Find min, that's easy. Just keep going to the left. But find min will be easy. Go to the left until we can't go left anymore. There, we found the smallest number. What about find max? This is easy, implemented recursively or iteratively. That's true. So yeah, just keep going to the left until you can't go left anymore. That's the smallest number. Find max, go to the right. Now the traversals are interesting. In a binary search tree, is there anything special about any of these traversals that are interesting to you? Have a look. And remember, pre-order is node first, then left, then right. In order is left, then node, then right. And then post order is left, then right, then node. And no one cares about level order. Just ignore that for now. So if you're to do these traversals, type in the chat as soon as you find something interesting about one of those traversals with a binary search tree. Because one of them's kind of neat. Which one? Prints out smallest to biggest. Which one? Which one? I mean, pre-order, in order to, there's 3 options. Which one? This one, or this one? Don't, what? What? It seems like you might be guessing or something. In order. Just remember how it prints. Okay, yeah, so it's the in order one. Why? Well, we go to the left, go to the left. All right, print out 3. Then go here, print out the 8. And then we go to the right, go to the left, print out the 9. Then the 12. Then we go back up to the 14. I guess I should add commas or something. Then we go to the right, then go to the left, then go to the left, nothing there. Okay, print out the 19. Go to the right, we got the 23. And then that's done. And then we go here, print out the 26. Go to the right. Whoa, that's supposed to be a 6, I swear. Go to the right, nothing there. Return, return, we're done. In order will actually print out the numbers in order. So that's cool. If it's a binary search tree. Okay, I am going to show you. Ooh, okay, this is exactly where I want it to be. I'm going to show you one last thing before we wrap up today. I'm going to try to show you one last thing before we wrap up today. Yeah. So a balanced tree. Wait. Has the property that for any node in the tree, the height of its left and right subtrees can differ by no more than 1. So, and remember that the height of an empty tree is -1. So, this is a balanced subtree. Or balanced subtree. This is a balanced tree, right? Because, well, the distance is no greater than 1. This is not. This is a problematic tree because the left subtree has a distance of like 2, or difference of 2. So which of these is balanced? Well, it's this one. So let's build a binary search tree with these numbers in it quickly. Well, okay, it's empty, so there's 3. And then we add 5, which should go to the right. And then we add 9, which should go to the right because it's bigger than 5. 12, 18, 20. Does this look like a tree to you? Because to me, I mean, sure, it's a tree by definition, but it looks a lot more like a list in my opinion. So if we built that, it looks like that. And this is what we call a degenerate tree. This is a problem because imagine I want to do a search on this. If I'm looking for the number 20, how many things do I have to look at? At every level in this tree, how many nodes do I get to throw away? Do I get to throw roughly half of them away? No, every time I go down, I only get rid of 1. All right, we'll talk about that in more detail next time. Anyways, that's all for today.